Hello and welcome to this video lecture on specific heats and the incompressible substance model. Go ahead and take a look at your screen. You see on the picture here we have a water jet cutter. So here is a nozzle and there's a thin stream of water. You can see it there coming out of that nozzle. That thin stream of water is coming out at very high speeds and it's cutting through what appears to be a plate of aluminum, I believe. I can't really tell what the material is, but you can see a cut here and it's cutting things out. Water jet cutters are pretty common now in manufacturing facilities. They're used all the time. I know that at Purdue, for example, in a lot of the undergraduate machine shops, they use water jet cutters to cut all kinds of different things. They're very powerful. And the reason I show it here is because normally when we model substances that are liquids, like water, for example, we treat that water as what's known as an incompressible substance, and we're going to talk about that today. An incompressible substance is one where the specific volume remains constant. In a water jet cutter, it's one of those rare instances where incompressibility is not the best assumption for the way the water behaves. It's because the water is at such a high pressure in the nozzle here, and then it comes out at such high speed that the compressibility does play a little bit of a role. But under normal circumstances, water and other liquids are treated as incompressible substances, and it's a model for sure. It's not the exact way real water or other liquids behave, but it's a very good engineering approximation, and that's one of the models we'll talk about today. In the next lecture, we're going to talk about the ideal gas model, which you probably already have some familiarity with. So we're going to talk a little bit about modeling. It helps us to move a little further away from having to use tables. And you'll see that in a little bit. Okay, so let's get started. First thing we're going to do is talk about specific heats. Now, specific heat is a property of a material. It's essentially how much energy you have to add to a unit mass of that material to raise its temperature by 1 degree. Okay, so how much energy do you have to put into it to raise a unit mass by 1 degree? And to give you an example of that, for iron, it takes about 4.5 kilojoules of energy to raise the temperature of iron by 1 degree Celsius. To raise the 1 kilogram of iron from 20 degrees Celsius to 30 degrees Celsius. So about 4.5 kilojoules to raise 1 kilogram of iron from 20 to 30 degrees Celsius. Now water, it takes almost 10 times that amount. It takes 41.8 kilojoules to raise 1 kilogram of water from 20 degrees Celsius to 30 degrees Celsius. So there's a different amount of energy to raise its temperature. Okay, and that property that describes the different amounts of energy that you have to add in is called the specific heat. We'll give the symbol specific heat a C here, and in general we talk about two different types of specific heat. One is the specific heat at constant pressure, the other is specific heat at constant volume. So when we add the energy into that substance, we have to say it's not just putting the energy in, but we have to describe the process that's involved. So one typical process would be to hold the pressure of the substance constant as we add in that energy, and the other is to hold the specific volume or the volume of the substance constant as we add in that energy. We won't go through the derivation of it, but the specific heat at constant volumes, is C sub V, is defined as the change in the substance's specific internal energy with respect to temperature as you hold the volume constant. So that's what the vertical bar with the subscript V means, is holding the volume constant during that process. And the specific heat at constant pressure is the change in the specific enthalpy with respect to temperature as you hold the pressure constant. So two definitions for the two different types of specific heats. And we'll see that ratio of C sub P to C sub V, that ratio of specific heats frequently in our analyses. So we give it a special symbol, we'll call it K, and that's what we call the specific heat ratio. Now, in general, the specific heats are functions of temperature and pressure. You can see that written here. But in our modeling, like the incompressible substance model and the ideal gas model, what we'll do is we'll say that in real life, for those kinds of materials, the pressure doesn't play much of a role, and so the specific heats are really a function just of temperature in those models. In general, it's a function of temperature and pressure in real life, but in the models that we use for incompressible materials and ideal gases, we just say that it's only a function of temperature. C sub P is larger than or equal to C sub V, typically. So, and the reason for that is when you put the energy into something at constant pressure, it can expand, right? Unlike constant volume it can't expand, right? But for constant pressure, it can expand. And so when you put the energy in, you're also doing some PDV type of work, right? So because it's expanding at constant pressure, the volume is expanding at that constant pressure. So some of the energy put in actually goes into PDV type of work. So you have to put a little more energy in to raise its temperature to that by that 1 degree. That's why C sub P is larger than C sub V in general, which of course means that the specific heat ratio is greater than 1 in general. As you'll see in a moment when we deal with an incompressible substance, since an incompressible substance is one that doesn't change volume, then C sub P and C sub V are the same, because the C sub P, you don't have that P to V work because it's not expanding, and so C sub P and C sub V are identical in that case. And we'll talk more about that in a moment. One number that's pretty useful to remember is the specific heat ratio for air. That's equal to 1.4. That's a number that we use so frequently, it's just worth memorizing. Okay. Now, one very important thing I want to highlight, just referring to this plot over here on the right-hand side, is when we talk about the specific heat at constant volume or specific heat at constant pressure, that does not mean that you're restricted to using C sub V only for constant volume processes or C sub P only for constant pressure processes. You can use C sub V and C sub P for any process. What it means is that what the C sub V and C sub P refer to, the constant volume and constant pressure, is just how that property would be determined locally at that point. So what I try to do here in this picture is show like a PV diagram, constant pressure process going from 1 to 2. So this is just some general process going from state 1 to state 2. And you can see as we go along that process, I can imagine locally, like here, kind of locally, this is what a local constant temperature path might look like, right? Do you remember if I just kind of sketch here on a PV diagram? Here's the vapor dome, and let me show an isotherm. Looks like that. So here's an isotherm. So you can see kind of in this region, it's heading down and to the right. So that's why I've drawn this down and to the right. And a constant volume path, of course, is just vertical. So you can see that as we move along in any sort of arbitrary path from 1 to 2, you can always consider just a local constant temperature path and a local constant volume path, for example, or a local constant pressure path, just locally. So I can have any process. Let me redraw that. Let's say point 1 is here and point 2 is here. And I go along some crazy path like that. Locally, I can always imagine a local constant pressure path, a local constant temperature path, a local constant volume path, and then calculate C sub V and C sub P locally. Okay, so I can still use C sub P and C sub V on that path. It's just that the C sub V and C sub P just mean that that specific heat is calculated for local conditions. If you just imagined at some point on this path what it would look like if you had a local constant volume or local constant pressure sort of process. But the whole process doesn't have to act that way. Okay, so don't feel, it's very important that you realize you don't have to use C sub V only for constant volume processes and C sub P only for constant pressure processes. You can use them for any kind of process. It's just the sub V and the sub P refer to calculating that specific heat locally in an imaginary differential kind of constant volume or constant pressure path. Okay, so hopefully that makes sense to you. You can find the values for C sub V and C sub P in tables. So I have a couple of tables here for different types of substances here and different other substances there. So if you look in this table, for example, you'll see the specific heat at constant pressure here, specific heat at constant volume here. You can see the values for air, ammonia, etc. They're specifically listed here for 300 Kelvin. as I mentioned a moment ago, in general, the specific heats are functions of pressure and temperature. When you deal with ideal gases or incompressible substances, we say that it's only a function of temperature. It is a good approximation. So that's why it's listed here as a function of temperature. The reason it's a function of temperature is because when you think about when you're putting energy into the material, as you put that energy in, that energy goes into changing the kinetic energy of the molecules involved. So some of that energy goes into the random kinetic energy of the particles. Of course, that's related to the temperature. But in more complex molecules, ones that have different atoms that are within the molecule, those molecules can have modes of vibration. So there's some energy that can go into vibration. They can also rotate, so some energy goes into that rotational mode as well, right? So when you put the energy in, it goes into all these different modes of movement of the molecules. And so that's why you have different C sub P and C sub V values for different kinds of materials, because as you put that energy in, depending on the molecular mass of the substance and how the molecules are arranged, the energy goes into different modes of the molecular movement. So some goes into the translational kinetic energy, some goes into rotational, some goes into vibrations. Okay, so that's why you have these different values, and which modes are activated depends to a large degree on the temperature that you're adding the energy into. And that's a more sophisticated topic, but I just wanted to give you a feel for why the specific heat values are different and they're a function of temperature. Oh, I guess another thing I should mention is the specific heat units that we typically encounter are in kilojoules per kilogram Kelvin. So kilogram and Kelvin are in the denominator. Again, it's how much energy you add, kilojoules, per unit mass to raise it 1 degree Kelvin. Okay. All right, I think that's all I want to mention about specific heats. Okay, so the next thing that we're going to talk about is the incompressible substance model. So far, we've talked about how to find properties using property tables. That's the most accurate way to find property values, is to use those tables. And there can be tables for all kinds of different substances. We focus primarily on water so far. Now, sometimes it's inconvenient to use those tables, especially if you're doing some kind of hand analyses and things like that. So we often create models for how materials behave. And one very common model is called an incompressible substance model. It's used most frequently when we deal with liquids and solids. Okay? And an incompressible substance model, the main assumptions that we make in that is that its specific volume remains constant. That's a big part of this model. In other words, the specific volume is constant right there in equation form. Okay? It means the volume of that substance does not change. And that's a pretty good representation for solids and liquids. You have to apply very large pressures to water, for example, in order for it to change its specific volume to any appreciable degree. If you go back and take a look at the PV diagram, or maybe the TV diagram, let me see if I can sketch that out. So here's a TV diagram for water, and this is going to be kind of a poor sketch here. Let me draw an isobar. So if I draw isobars here, and you're better off taking a look at a previous video lecture where the actual plot is shown. But what I want to point out is that this is as pressure increases. What you'll find is that the isobars are really close together in that compressed liquid region. Right? These isobars are really jammed close together here, meaning that you can change the pressure quite a bit. You can bounce around between different pressures here, and it only makes a very small change in the specific volume. Right? So they're just closely packed together. So what that means is that even though you change the pressure a lot, specific volume remains about the same. Same sort of thing if you change the temperature over here. It just doesn't change the specific volume very much at all. So we'll just make the approximation for an incompressible substance that the specific volume just remains constant. Okay. Now the other part that goes into that incompressible substance model is that the specific internal energy is a function solely of temperature. So that's this part right there. That specific internal energy is only a function of temperature. In general, it's a function of temperature and pressure, but for this particular model, we'll say it's just a function only of temperature. So with that being the case, remember that the C sub V is just defined in general like this, right? It's the change in specific internal energy with respect to temperature at constant volume. That's just coming from right here. Well, let's do that calculation for an incompressible substance. Since the internal energy is only a function of temperature, it just means instead of being a partial derivative, it'll just be an ordinary derivative. And at constant volume, well, it's a constant volume already. It's an incompressible substance. So our C sub V just becomes that. The partial, remember, a partial derivative indicates that it's like U here would be a function of more than just temperature. It might be temperature and pressure, for example. If it's an ordinary derivative, it means it's only a function of temperature. Okay, so then we see that it's only a function of temperature, which then means that CV, of course, is only a function of temperature as well. Let's do let's do it for the C sub P. Before I do that, let me just expand out the specific enthalpy. Remember, the specific enthalpy looks like this, right, in general. And since we're dealing with an incompressible substance, the U is a function only of temperature. And of course, V is a constant, right? So when we calculate C sub P, which would be like dH dt, constant pressure, since the pressure is a constant, this whole thing is a constant. So when we take the derivative with respect to temperature, we'll get the following. Since the pressure is a constant here, the specific volume, of course, is a constant, and the specific internal energy is only a function of temperature. So when we take the partial derivative of H with respect to T at constant pressure, it looks just like du dt, which we found previously to just be equal to CV, which in general is a function of temperature. So what we get from all of this is that Cp is equal to Cv, both of which are functions of temperature. And just to save ourselves a little bit of writing, we'll just write it as C rather than the subscript P or V. And just a reminder, that's in general a function of temperature. So the specific heat for an incompressible substance is only a function of temperature, and there is no specific heat at constant pressure and specific heat at constant volume. It's just a single specific heat. Now going back up to this expression, we can rewrite that in the following way. Okay, I'm just using a C instead of a CV here. If we integrate both sides, as we go from some initial specific internal energy to some final value, here we'll go from some initial temperature to some final temperature. Remember that the specific heat is in general a function of temperature. So this will look like U2 minus U1 is equal to the integral of C, which is in general a function of temperature, dt. So that is how we can find the change in the specific internal energy for an incompressible substance. We don't need to go back to the tables for a compressed liquid. We could use this expression, but what we need to do is we need to know what the specific heat is for the substance we're dealing with. And in general, it's a function of temperature. Now, if the temperature doesn't vary by a whole lot, then the specific heat likely won't vary very much either. And so we can rewrite that expression as, let me just write it as delta U is C delta T. So this is if C is approximately equal to a constant, so it's not a function of temperature. That's generally the case if you're dealing with small changes in temperature, like a couple of hundred or a few hundred Kelvin. In that case, then we have this approximation. So this is an approximation. This is a more accurate expression for finding the change in the specific internal energy. So you're better off using this as opposed to that. But if you're dealing with small changes in temperature, then this one's okay. It's fine to use. Now let's go back and look at the expression for the specific enthalpy. We can write that in the following way. H2 minus H1 will just be U2 minus U1 plus P2 minus P1 times the specific volume. So all I'm doing is just taking this expression, writing it out for state 2 and state 1. And notice here that I didn't expand V into V2 and V1 because specific volume is just a constant. And then we could rewrite that if we wanted to in the following way. So this is how we could find the specific enthalpy change between two states. And again, if we're dealing with small changes in temperature, where we could neglect the dependence of the specific heat on temperature, then this expression just becomes delta H is equal to, this would just be C delta T plus delta P times specific volume. So that again is if C is about equal to a constant, which would be the case if you're only dealing with a couple of 100 Kelvin temperature difference, so small enough to where the specific heat is reasonably assumed as being a constant. Okay, I think that's everything I want to say about the incompressible model. This is a model we'll use very frequently, so make sure you understand how to use it. We'll talk about the ideal gas model in the next video lecture, so we'll end it there.